Hi everyone, and welcome to this week's seminar. It's a pleasure to have Marine Carrasco with us, and Katsumi. Thanks a lot for joining. For accepting. Marine for accepting to give the talk, and Katsumi to be the discussant for today. Marine will present score type tests for Markov switching models. So you have 1 hour, and then the audience may interrupt with the questions, and then we leave some time after 1 hour for Katsumi if he has more comments or remarks on the paper. Marine, thanks a lot again, and the floor is yours.
So thank you very much for inviting me to this virtual time series seminar. It is a pleasure to present my work. It's the first time I'm presenting this paper, so I welcome all comments you may have. So this is a joint work with Dante Amengar, Shinui Bei, and Enrique Santana. And we are proposing a test for Markov switching. So Markov switching models generalize finite mixture distribution to dynamic context in which observations are seemingly clustered in time in a small number of recurrent regimes. So it originally was introduced by Goldfeld and Kant, and it became popular thanks to the work of Hamilton, who extended this model to autoregressive specifications and applied them to interest rates and aggregate output. So here are a few references. For textbook treatments, we refer the interested readers to Hamilton, to a book by Hamilton, Kreutzig, Kim and Nelson, and Frühwirth-Schnatter. And there are some useful surveys of applications to macroeconomics and finance by Hamilton, Guidolin, Eng, and Timmerman. So here we are going to focus on a relatively simple model. Under the null, the process is drawn from a normal distribution. And under the alternative, process is drawn from a two-regime Markov switching model with a Gaussian shock within each regime. So we're focusing on the Gaussian case. And actually, a Gaussian case is a difficult case for various reasons. So if for instance, we want to study the properties of a likelihood ratio test, it turns out to be very challenging for two reasons, basically for one theoretical reason and one practical reason. From a theoretical point of view, it is difficult to derive the distribution because there are several ways to approach the null. So there are basically two main paths for approaching the null hypothesis, and some parameters are typically not identified under the null, and some parameters that are identified are only identified at a higher order. So there are some technical issues here. But besides the theoretical problem, there is also a computational issue. If you want to implement the likelihood ratio test, one of the difficulties you encounter is finding the maximum of a log likelihood is numerically difficult when the null is true. So basically what happen is that the likelihood is flat under the null, and it is difficult to find the maximum. So there are basically two problems, one theoretical and one practical problem with implementing the likelihood ratio test. So instead of focusing on the likelihood ratio test, we propose score type test. So the advantage of a score type test is that it requires estimating the model under the null only, which is an advantage. And we don't propose any test. We want a test that is equivalent to the likelihood ratio test. So we are going to base our score type test on a higher order expansion of the likelihood. So our contributions are, besides proposing this new test, we are going to derive its asymptotic distribution under the null and the local alternatives, and we show its equivalence to the likelihood ratio test. And then we are going to establish the asymptotic admissibility of the test, meaning that we are going to show that the test we propose is the best for a certain alternative that we are going to document. So this is for the introduction. We give a brief review of literature. So it turns out that some of the problems we encounter when we test for Markov switching appear also when testing for independent mixture. So what initially we wanted to start immediately with testing for Markov switching, and we found out that it was actually already very difficult to address tests for independent mixtures. So we basically decided to first investigate tests for independent mixture. So here are some of the references for tests for independent mixture. So in statistics, there's Azais, Garciat, and Marcadier. In econometrics, Shaw and White, 2007, who want to test for Markov switching, but actually base their test on independent mixture. There's a paper by Xiaohong Shen and Eli Tamer, 2014. There's a paper by Kasara and Shimotsu, 2015. And more recently, our paper published in Journal of Econometrics in 2025, where we test for independent mixture. Again, here in this paper, the null hypothesis is a Gaussian process, and the alternative is a Gaussian mixture. So now I'm giving some references for likelihood ratio test, likelihood-based test for Markov switching. So the first contributions are by Bruce Hansen, 92-96. Then there's a paper by René Garcia, 98. And the two papers that are the most closely related to what we are presenting here are the paper by Kasara and Shimotsu, 2018, who test even multiple regimes. So it looks at the distribution of likelihood ratio test for testing potentially 2 versus 3 regimes. And it's not confined to the normal case. And a paper by Xu and Zhu, 2021, who also investigate likelihood ratio test here for 2 regimes, I think. And then recently, there's a paper by Rodriguez, Mondo, and Dufour, who propose Monte Carlo tests for Markov switching. So the Monte Carlo tests are tests based on simulations. These are exact tests, so the size is controlled under the null. and it doesn't rely on the asymptotic distribution. So it's a bit different from what we are doing here, because we are interested in the asymptotic distribution of our test. And finally, of course, what we are presenting here is correct, related to a previous paper by myself, Hu and Werner, Liang Hu and Werner Ploberger, published in 2014, where we propose a score type test for Markov switching. So this is similar in spirit, but we are going to see that the test proposed here doesn't consider all the null hypotheses. It considers only one part of the null hypothesis, and hence it may lack of power against some alternatives. So we are basically extending this work. So we can see the current paper as an extension of Carrasco, Hu, and Ploberger, and an extension of our previous paper from the independent mixture to Markov switching models. So the model, as I said, is a very simple model. I'm going to start with the simplest possible specification of under the null. The model is just the YT. The observations are just drawn in a distribution with constant mean and constant variance, and more importantly, the distribution is Gaussian under the null, and under the alternative, we have a mixture of two Gaussians. So where the mean is allowed to switch according to an underlying process, Markov chain ST, which is not observed. ST is a Markov chain that drives a change of regime and is not observed. And sigma ST, so the variance, is also allowed to switch according to the unobserved Markov chain. So we focus on the case where the Markov chain can take only two values, 0 and 1. And the transition probabilities are denoted P and Q. So in practice, of course, P and Q are not known, the Markov chain is not observed, mu and sigma are not known. And as I say, under the null, the process is drawn from ID normal mu sigma square, and under the alternative, we have this change of regimes driven by a latent Markov chain ST. So in this representation, using this notations, the set of parameters is this, but we'll see later that it's more convenient to change the parameterization, and we'll have different notations of our parameters. We, to avoid any problem with initial values, we assume that the initial value S0 and Y0 are drawn from distributions that are that may depend on some parameters, but these parameters are not related in any way with the parameters of interest phi. So this is the initial model. And I first need to introduce some notations. And as I said, we are going to use reparametrization. So notations. So it's important to introduce a notation lambda, which corresponds to the stationary probability to be in regime 1. And by convention, because the labels of the regimes can basically be exchanged, we are going to assume that lambda is greater or equal than 1/2. It's just to say that the regime ST equals to 1 is the most frequent. So we see that if lambda is equal to 1, here we are always in regime 1 and there is no switching, right? Another notation that will be useful is the notation rho, which is the autocorrelation of a Markov chain, and just happen it can be it is equal to p plus q minus 1. But this is important because if rho is equal to 0, there is no autocorrelation, and we are in the case of independent mixture. And this is the case we want to allow in our paper. So we are not ruling out the possibility that rho equals to 0. So then we denote mu the unconditional mean of yt, and sigma square the unconditional variance of yt. Now, it is convenient to introduce the notations delta and var kappa. Delta is basically proportional to the difference between the means in the two regimes. So we see if the mean is the same in the two regimes, so mu naught is the mean of yt in regime 0, mu1 the mean of yt in regime 1. If these means are equal, then delta equals to 0. So testing mu1 equals to mu2 is equivalent to testing delta equals to 0. And here we introduce the notation that I call var kappa, which is the log of a ratio of a variance. And we see that if the variance is the same in both regimes, then var kappa equals to 0. So basically, the null hypothesis, one of the null hypotheses of interest will be delta equals to 0 and var kappa equals to 0. It turns out that, and we'll see it later on, that the value of mu and sigma square doesn't affect the test statistics. So for now, at least for the beginning, I'm going to assume that mu and sigma square are known and equals to 0 and 1. So for the marginal distribution, so for unconditional distribution, the mean and variance is 0, 1, and they are the same under the null and the alternative, which is not something that everyone does, but it will permit to confine the alternative to the Markov switching and not to a change in mean and variance. So we assume for now on that the mean and variance are 0, 1, and later on I will address the issue of estimation of mu and sigma square. So now we are introducing yet again a reparametrization, which is used also in Amengal and in our previous paper, and is useful to so that the derivative of a log likelihood with respect to the parameters is 0 so that the first derivatives are 0. So it's a technical, for technical consideration, we introduce this reparametrization. So now our parameters are delta, kappa, lambda, and rho. And so you have to keep in mind that delta equals to 0 is if the means are equal across regimes, and kappa will be 0 if the variants are the same across regimes. So what is special about testing for Markov switching? One aspect which is really specific is there are two ways to write the null hypothesis. The first, we can either test the equality of means and variances in both regimes. So this is what I denote H naught A. And you can write it as delta equals to kappa equals to 0. So here you test that the mean is the same in both regimes, the variance is the same in both regimes. And what happens in this, under this null hypothesis is that some parameters are not identified, namely lambda and rho are not identified under the null. So this is one first difficulty. And a second difficulty is that the first derivatives of the log likelihood are exactly 0 under H naught. So you have, it happens that some parameters are not at all identified, but even the parameters that are identified are only identified at a higher order. And this will imply some unusual rate of convergence for the local alternatives, as discussed also in Dovono and Renaud. So this is the first way to write the null hypothesis. The second way to write the null hypothesis is in terms of lambda. So lambda, I remind you, it's the probability to be in regime 1. So you can test whether this probability is equal to 1 exactly. If it is equal to 1, once you stay always in the same regime. And if you are always in regime 1, well, obviously you cannot identify the parameters delta, kappa, and rho. So you have, again, the problem of some nuisance parameters that are not identified under the null. And moreover, here lambda is on the boundary of parameter space because lambda is a probability. It has to belong to the interval 0, 1. So necessarily under the alternative, lambda is smaller than 1. So these are the two ways to write a null hypothesis, and we want to actually address these two ways and not just consider one of them. So in many papers, people choose one of these two null hypotheses and focus on one of them. So, for instance, in my previous work with Liang Hu and Werner Ploberger, and also in papers by Kasara and Shimotsu and Shu and Zhu, they focus on testing equality of means, equality of variance. And moreover, all these papers assume that then lambda is bounded away from 1. So we assume that lambda is strictly smaller than 1. On the other hand, there are some papers in statistics in particular that focus on testing lambda equals to 1 only, and they don't consider this case. And they look at testing lambda equals to 1, but they restrict the parameter space to values of delta and kappa away from 0. So in that sense, even if you address this two null hypothesis, you see that one part of the parameter space is ignored. This is the part where simultaneously you have delta and kappa equals to 0 and lambda equals to 1. And if you basically discard this part of the parameter space, your test may not be equivalent to the likelihood ratio test. So this is something we want to avoid, and we want to consider both null hypothesis and the whole parameter space. Another motivation to look for looking at this null hypothesis, which is lambda equals to 1, is that in practice, in many empirical applications, actually it is observed that the estimated values of lambda are close to 1. And this was noticed in a paper by Charles Engel. So we are going to look at these two null hypotheses. Here is a drawing of a parameter space. When you are interested in testing delta equals to kappa equals to 0, usually people discard the values of lambda close to 1. So it means that they look at the parameter space, which is a kind of truncated cube here, if we represent the parameter space as a cube. Similarly, people that have been testing lambda equals to 1, they usually ignore values of delta and kappa close to 0. So they look at a parameter space, which is like a donut with a hole in the middle. And now if you combine both approaches, you are still missing one part of the parameter space, which is the zone where delta kappa are close to 0 and lambda is close to 1, converges to 1. So this is this part that I will refer to as corner part of the parameter space, and that we want to incorporate in our testing procedures. So to do so, to be able to consider not only the two null hypotheses, but the whole parameter space, we partition the parameter space into two pieces. So our goal is to construct a score type test equivalent to the likelihood ratio test. So this is the likelihood ratio test. And we are going to partition the parameter space, which I denote theta, into two pieces. One piece that we are going to call the pyramid is a case where delta and kappa is smaller than 1 over lambda. And the other part of the parameter space are the cases where delta and kappa is greater than 1 minus lambda. So it gives a strange shape to the two spaces, but it will permit to test the two null hypotheses on two different spaces, basically. On PA, we are going to test delta equals to kappa equals to 0, and on PB, we are going to test lambda equals to 1. So what does it look graphically? So after our parametrization, our parameter space has this shape. It's not a cube, actually, as I showed before. It's more this. And as I say, we partition this parameter space into a pyramid and the rest. So the pyramid is this zone. And this is within this zone, which we denote PA, that we are going to test delta equals to kappa equals to 0. And it is on top here that we are going to test lambda equals to 1. So outside of the pyramid is PB, is where we are testing lambda equals to 1. And as before, we have to be careful. There is an area where delta and kappa are close to 0, or maybe exactly 0, and lambda equals to 1. And this is the tricky part that we have to address, because we don't want to discard any part of the parameter space. So first, we're looking at testing for equality of means and variance. In terms of our notations, we are testing the null hypothesis H naught A, delta equals to kappa equals to 0. And as I say, we can confine the parameters within the pyramids, so within the space PA. It turns out that under this null hypothesis, the derivatives of the log likelihood, the first derivatives of log likelihood are 0. So that basically the rate of convergence are not the usual root t, but much slower. And there are two ways to approach the null hypothesis. So, and these two ways are displayed here. In the first set of conditions, we see that rho goes to 0 at a certain rate, and delta kappa go to 0 slower. At least delta goes to 0 slower than rho. So basically, this first line includes the ID mixture, because we could have rho equals to 0 exactly, which is the ID mixture. And this will give us first test statistics, which we denote LMA1. And the second set of conditions, we see that rho now can be constant, and delta and kappa go to 0 faster, but still slower than rho t. And this gives us the test LMA2. So we have two tests, which will be basically designed to test these alternatives. And we combine these two tests by taking the maximum, and this will be LMA. And these two paths to approach the null hypothesis corresponds to properties of unconditional distribution. Typically, for this path, the unconditional distribution under the alternative is platykurtic, and for this path, it's leptokurtic. So first, we are looking at the first set of conditions, which I remind you is a case that encompasses the independent mixture. This is a difficult case because to be able to provide a test equivalent to the likelihood ratio test, we have to do an 8th order expansion of the likelihood. But it turns out that at the end, the expression of the test statistics is relatively simple and actually very familiar. So it will depend on Hermite polynomials. So we denote H3, the third Hermite polynomial, H4, the fourth Hermite polynomial. And with the bar, it's a sample mean of these Hermite polynomials, and our test statistics as this sample expression. So we recognize here the squared third Hermite polynomial, which I remind you has power against skewness. So if the distribution is skewed, this part will pick it up. And here we have a fourth Hermite polynomials, which has power against leptokurtic or plateaukurtic distribution. But here, because we have this inequality, it means we are focusing toward the plateaukurtic alternative, which are distributions that have thinner tails than the normal distribution. And finally, this part of the statistics involve the correlations, the autocorrelations of YT. So we see where the power will come from, right? From a correlation of YT, from the skewness and the plateaukurtic properties of the alternative. And so why we focus on plateaukurtic alternative? It's because for this strange alternative, this is the unconditional distribution of YT is necessarily plateaukurtic. As I say, this case includes a special case, an independent mixture case, which is also of interest and has been addressed in our previous paper. And just for comparison, I remind you the formula for the LMAT test in the paper, in our previous paper, and it is really simple. It's exactly the Chark and Bera test statistics, but involves the third and fourth Hermite polynomials. So, and we see that we have something similar here. So this is for the first part of the test. The second part of the test, LMA2, I remind you now we have conditions which for which rho could be actually under the alternative rho could be non-zero, and turns out that the second test, LMA2, coincide as two interpretations. It can be viewed as the test of for serial correlations against ARMA 1-1, as in Andrews and Kloberger 96, and it coincides also with the test proposed in Carrasco and Kloberger 2014. So here I'm going just to remind you what is the test in Carrasco and Kloberger. It's a test which is based on the fourth order expansion of the likelihood, because in this paper, we explicitly rule out the case where rho could be zero. So we rule out the case where we could have independent mixture. And the test is based on quantities that depend on the derivative of the log likelihood. So we see here the second derivative of the log likelihood, and here the product of the score squared. So this part can be interpreted as the information matrix test, because it will be a martingale difference sequence under the null. And this part involves a correlation between the scores, and this is also a martingale under the null, so that the test actually converge to a Gaussian process under the null, and will have power against alternative for which there is correlation in the score, or for which the information matrix statistics is different from zero, basically. So the statistic in Carrasco and Kloberger is this. It involves the sub over the nuisance parameters that are not identified. And in the denominator here, this quantity may look strange, but it's actually a consistent estimator of the variance of a statistic. So what we have in the current paper is basically the same thing, except for the denominator. Here, our denominator is the exact variance, because we are able to calculate the exact expression of the variance, while in Carrasco, Hu, and Kloberger, it's an estimate. And of course, when mu and sigma are not are unknown, then mu and sigma are estimated, and then you replace yt by the standardized version of yt. So this gives an intuitive interpretation of the test statistics. Are there questions so far?
No question for the moment, I think.
Okay.
Thank you.
So these are the two test statistics we have for testing equality of means, equality of variance, and the two test statistics basically depend on how rho goes to 0, the correlations between the process. And then we combine these two test statistics by taking the maximum, and we show that we have equivalence with the likelihood ratio test. So our LMAT test is equivalent to the likelihood ratio test that will be confined to PA. Now, so this is for the first test. Now we are considering the test of lambda equals to 1 against the alternative lambda less than 1. So we see that we are at the boundary of the parameter space, and there are some nuisance parameters that are not identified under the null, and these nuisance parameters are delta, kappa, and rho. So we denote the score as GT. The score is the derivative with respect to lambda here. And first, to simplify a bit the exposition, we first assume we are away from the problematic case where delta and kappa are 0. So assume that delta and kappa are away from 0, where the norm is greater than an epsilon. In that case, we are really in more or less a standard setting where the score with respect to lambda converge to a Gaussian process with mean 0, and we have we can construct a test based on the maximum of our statistics with respect to the nuisance parameters that are not identified under the null. So this looks very much like a test of Davis and Andrews and Kloberger. We take the maximum over the nuisance parameters, and we have the statistics which converge, for which we can apply the continuous mapping theorem, because the process is stochastic equicontinuous, and it will converge to the maximum of a Gaussian process, where we take the minimum between 0 and the statistics, because it's a one-sided test, and the square here. So this is more or less a standard case. The problematic case is a case where simultaneously we have lambda equals to 1 and delta and kappa equals to 0. This is the corner case which has been omitted in previous papers, and we want to explicitly address. So here, how do we do to handle this case? It turns out that the score, when delta and kappa are 0 and lambda equals to 1, the score with respect to lambda is exactly 0. And hence, its variance is exactly 0. So now we have a kind of discontinuity in the process GT. GT was converging to a Gaussian process, and now we have a discontinuity, which makes that now the process is not stochastic equicontinuous for this part of the parameter space, and we cannot apply the functional central limit theorem. So to deal with it, we did a change of again, a change of variable. We reparameterize to so we change, instead of working with GT, we work with GT over tau, where tau is a function of the parameters such that tau goes to 0 if and only if delta and kappa goes to 0. So in some sense, we reparameterize the model so that now the quantity gt over tau is well behaved. And now we get back to the stochastic equicontinuity and functional central limit theorem. Once we have transformed our process by dividing this tau, which converges to 0. So it's a bit like an L'Hopital rule. You have 0 over 0, but it works. And then because we have the one-to-one transformations, we can basically address the whole parameter space. But it comes at a cost that we have to go to a higher order expansion again and to address this part. So now we can claim the result for the whole parameter space PB. Our test statistics is this one, where now we have included the corner problematic case, and we show the equivalence between the likelihood ratio test and the LM test for the whole part of the parameter space PB. So now we have two tests, right? We have LMA and LMB. And because we have partition, because theta is a partition, has been partitioned within PA and PB, then a way to combine this test is just by taking the maximum. And we have equivalence between the two test statistics. So we show that our score type test is equivalent to the likelihood ratio test. And interestingly, even so here we have a max between two statistics, it turns out that LMBT is always greater or equal than LMAT. So it means that we can simplify the calculations in one sense. Instead of calculating both statistics, we could just focus on LMBT. And of course, in some cases, LMAT may be still useful and may even potentially have more power than LMBT if the alternative is specific. So, but we have this result, which is a numerical result, and is true whether we are under the null or the alternative. So LMBT is always greater than LMAT. So local alternatives. Maybe I'm going to summarize these slides with the following table. We have seen already what the local alternative look like when you want to test the equality of means and variance. These are unusual rates of convergence here. And we have seen the test statistics that we got for these two sets of local alternatives. For testing lambda equals to 1, the local alternative is standard. It's at a rate t minus 1/2. So local alternative takes this form, lambda equals to 1 minus h t minus 1/2, and the test statistics takes this form. So we have basically 3 test statistics. But as I said, the dominant one is LMBT, and we show in the paper we actually derive the distributions of these different test statistics under the null and under the local alternatives. And we show that the tests have a non-trivial power, and they are consistent in the sense that the power converge to 1 against fixed alternatives. So if you are away from the boundaries, so lambda is away from 1 and delta and kappa are away from 0, our test statistics diverge, and then the power goes to 1. So robustness to parameter uncertainty, of course, this is very important issue. So far, I assume that mu and sigma square were known. In practice, of course, we are going to estimate them, and a natural estimators is just to use a sample mean and sample variance of white. And it turns out that actually this step of estimating mu and sigma doesn't have any impact on the distribution and on the test statistics. So the distributions of test statistics remain the same, and the test statistics can be implemented as before. The only thing, you just replace YT by a standardized version of YT, where you center YT by the sample mean and divide by the sample variance. So the results remain the same. And it is important to notice that the null asymptotic distribution of the test statistics is the same whether mu and sigma are known or estimated. So a word on admissibility. So we have really tried to devise a test which was equivalent to the likelihood ratio test. However, there is no results claiming or that can be used really to claim that likelihood ratio test is the best, because we know there is no most powerful test in this type of non-standard setting, and the optimality of the LR test hasn't been investigated in this particular case. So I quote here some papers that we are using, but they don't address exactly the same problem. So Andrews and Proberger established asymptotic admissibility of likelihood ratio test for two-sided alternative when some nuisance parameters are not identified under the norm. Here we have a one-sided alternative. And Andrews 96 focus on cases where the parameter space is restricted under the alternative, but there is no problem of parameters not identified under the null. So in our setting here, we have some difficulties which are a bit different from those addressed by Andrews and Proberger. So Andrews, we are at the boundary of the parameter space and some nuisance parameters are not identified. And we want to show the admissibility of our test statistic. Given we have seen just before that LMT coincides with LMBT, we focus simply on the admissibility of LMBT. And to do so, well, I first need to define what I mean by admissibility. So we focus on the local alternative of this form. A test fight is admissible if its power is maximum. So it maximizes a weighted average power with respect to some prior. So basically you have to be a bit Bayesian here. You have to assume some prior on H, which is appears in the local alternative here, conditional on pi, and some prior on pi, which is the new set of nuisance parameters, which are delta, kappa, and so basically a test is admissible if there are some priors on H and pi for which this test maximizes the power. And for this specific alternative, then the test is the best possible test. And then the way we proceed is really a bit inspired from the papers by Andrews and Proberger. We are selecting, so it's a bit special here because H is a scalar. So basically our prior on H reduces to a mass point, which is depends on R, which gives us the distance to the null, basically, times the information matrix. And J here actually can be an arbitrary positive probability measure on pi. And for these priors, we show that the test based on LMT is the best in the sense that it maximizes the power. So it beats any other test. So it shows, but we see that there is a condition on R here. R has to be greater than some constant R naught. So what we say is R naught, there exists a constant R naught such as for all r greater than this value, that our test is the best. So it means basically that our test statistic is optimal for alternatives sufficiently distant from the null hypothesis. And because we have equivalence between LM and LR, we can deduct also the admissibility of the likelihood ratio test, which was not known and is a new result because this case had not been considered previously. So this gives a justification for working on this type of test statistic. So in the paper, we have an extension to an autoregressive model with switching constant, switching variance, but constant autoregressive coefficient. Otherwise, the model is the same. We restrict ourselves to Gaussian error. And what is new here is now the estimation of alpha will have an impact on the distribution of the test statistics, contrary to what we had before. And to make our score test immune to the estimation of alpha, we have to adjust the statistics by projecting first on the different elements of our test statistics on the score with respect to alpha. So this will remove the impact of estimation of alpha on the test statistics, and then we proceed as before by showing that our test statistics are equivalent to the likelihood ratio test. So now I'm going to show simulations. I'm going to focus to the Gaussian case. On the Gaussian case, so no autoregression here. The mean and variance are unknown. We are estimating them using sample mean, sample variance. What I'm going to report are size-corrected power. So we are going to compute empirical critical values based on parametric bootstrap. Parametric bootstrap here consists simply in drawing samples on the null hypothesis. So here the null hypothesis is just ID, and given mu and sigma square are unknown, we replace this unknown mu and sigma square by sample mean, sample variance. This way, we can generate a large number of samples under the null, so 10,000 replications here, which will be used to compute the empirical critical values. And then we draw 5,000 samples of size 250 to assess the power and compute the size-corrected power. So the theoretical size is 5%, and this is what we get. This is a bit small. We see that the power really depends on the null hypothesis. You may be surprised here the power is not very high, but it's because we have no skewness, basically very little kurtosis, and here we are under the ID mixture. So basically tests like LMA doesn't have LMA1 doesn't have much power. No, it's actually LMA1 that should have more power, but here we have a bit of power here and a bit of power here. But what is more interesting, of course, is when we are further away from the null hypothesis, we see we have more power. So what could we conclude from these simulations? Well, when lambda is close to 1, this is LMB, which would be most useful because LMB is testing lambda equals to 1, and it's what we observe in the simulations. LMB is usually more powerful than LMA when lambda is close to 1. Even so, we said that LMB is greater than LMA, and by construction, LMA is greater than LMA1. It's not always the case that LMB is the most powerful test. Why? Because basically, first, this inequality means that the critical values will be different for the different tests. So LMB is bigger, but also its critical value is bigger. So it's more difficult to beat. And also, it depends really on the alternative. For some alternative, this test will have more powers for some alternatives, and it just can happen that some alternative would favor one test over the other. So in one sense, it's useful to investigate several tests. And for many cases, we beat the likelihood ratio test, but not always. And here again, we have equivalence with the likelihood ratio test, so it's not surprising, but sometimes we don't beat it. So just because I don't have much time, I'm going to briefly mention the application. We applied our test to test whether there is some Markov switching in the log difference of exchange rates. So we looked at different currencies, so British pound, Swiss franc, Japanese yen, and Deutsche Mark, which becomes euro later on. And we find that we actually reject the null hypothesis for two of these currencies, British pound and Swiss franc. And interestingly, you see that the value of lambda here for Swiss franc is very close to 1, and also for the two other currencies. So here we are in a case where lambda is very close to 1, and then it's preferable certainly to do the test of lambda equals to 1 than the other one. And this is actually what we see here. The p-value of the test LMB is very close to 0. So you reject strongly the null hypothesis lambda equals to 1, but you don't reject the null hypothesis of equality of means and variance. So if you were doing only the first test, you would not reject, while by doing second test, you reject. And so we reject more strongly than the LR test, but the LR test also rejects. So it seems there is a switching in the British pound and Swiss franc. And if you look at the parameters, you see the switch is mainly in the means here. There is not much switch in the variance, a bit in the British pound. So, I'm going to conclude. So we propose a score type test for testing a null hypothesis of ID Gaussian random variables against a Gaussian Markov switching alternative. We want to address the two ways the null hypothesis can be written, and we don't want to discard any part of the parameter space. We show the equivalence with the likelihood ratio test. We show also the admissibility of the test. Of course, we focus on a very simple model. It would be interesting to look at more general models. And it would be in particular interesting to look at multiple regimes, and as in Kasahara and Shimotsu. An extension also that could be interesting is to look at exponential type tests, like in Andrews and Ploberger and CHP. And it would be nice to go beyond the Gaussian distribution, so to look at Markov switching model for non-Gaussian distributions. So thank you very much.
Thank you very much, Marine, for the great talk, very clear one. So I'm going to invite Katsumi if he has some comments, remarks, and then open the floor for the audience if they have more comments.
Thanks.
Thank you.
Should I remove, should I stop sharing? Or?
Actually, I have slides.
Okay.
So, okay.